Alright, so we've had a look at decimal number systems, and just a reminder, we have our decimal number line counting up the thousands and the tens to the hundreds to the thousands, and our binary number systems where we count up in doubles of 2, so 2, 4, 8, 16, etc. Now we're going to have a look at hexadecimal and octal. So hex and octal numbering systems are used in computing, octal less so nowadays, but hex definitely so, as ways of controlling the numbers of ones and zeros that we get smashed in front of us when we're looking at binary systems. And so therefore we'll often see hex come up in terms of computer errors. Your blue screen of death will contain a hex code, or a bunch of hex code, which is actually memory addressing for where the error occurred. So whilst you can't necessarily read the exact minutiae of what's being said, if you submit that to Microsoft, they'll be able to analyze that memory addressing and codes and work out what caused the memory conflict through those hex codes, through that understanding of memory. So the first thing we're going to do is we're going to start looking at how to understand and interpret hexadecimal. And in fact, hexadecimal is a really simple numbering system once you get beyond the fact that there's more than 10 base numbers. What do I mean? Well, when we're doing our counting in decimal, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Should start at 0, sorry. And they're our base numbers in decimal. And the next number we start compounding at 10, etc. But I already said there are 16 base numbers in hexadecimal, and we've only got 10 so far. Because we don't have 6 other base numbers, we steal from the alphabet. So we have A, B, C, D, E, and F, and there's our 16 base numbers. So when you're writing a number in hex, you often see a hex address like 3F9. And actually, let's just go back to ASCII and Unicode. You might recall here 047C is a hex number. Well, the reason why that number 047C or whatever it was is used because that value there. And we'll start to understand soon why that comes up. 3F9 is a fairly well-known hex code as well. So when we have a decimal number and we want to convert it into a hexadecimal number, doing it in one step is nigh on impossible. But actually it's really simple to do. There's 16 values. So we create a table. We create a table of hex to binary. Hex to bin table. And it's always 4-bit ASCII. 4-bit, I beg your pardon, it's 4-bit binary. 4-bit binary always. And it's quite simple. So we have our binary, we have our hex. And just to make it a bit easier to read, I'll do it across 4 columns. Okay, so let's try that again. So I have my binary codes, and I'm just counting up. Of binary values that we can get from 4-bit binary. Right? 4-bit binary, there's only 16 values, and each of these has a hexadecimal equivalent. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now 1010 isn't 10, not in hexadecimal. It's A, B, C, D, E, F. This table is the first stage of any conversion between hexadecimal and decimal. Always start with 4-bit binary to give its equivalent hex value. So when you are seeing 0101, you can see that's 5. 1110 is E. So that we can turn any hex value into its equivalent binary almost instantaneously. So let's go back up here and look at this Unicode value. 047C. So hex 047C. You will see how quick this is. 047C. So what's 0 in binary? 0, 0, 0, 0. What's 4 in binary? 0, 1, 0, 0. 7 in binary? 0, 1, 1, 1. And C, 1, 1, 0, 0. So we've just turned a hex code into its equivalent binary instantaneously. It's that quick. Let's do a quick aside while we're here. You can do the same with octal. So start with the binary, and the octal. So the binary starts at 0, 0, 0. This time it's only 3 bits. 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, and 1, 1, 0, and 1, 1, 1. There should be 8 of them. 1, 2, 3, 4, 5, 6, 7, 8. Yes, I've got it right. So once again, 0, 1, 2, 3, 4. Learn to type, or learn to write. 4, 5, 6, 7. And so therefore any binary code, any octal code that we get, we can also turn into binary really, really quickly. So if I have an oct code, 214, it doesn't matter. It says it's an octal code, so I can turn it into its binary. Again, 214, using this table up here, so it's got to be 3-bit only. 2 is 0, 1, 0, 1 is 0, 0, 1, and 4 is 1, 0, 0. Once again, I've just turned an octal code into its equivalent binary almost instantaneously. That's pretty cool. Okay, so it's possible to convert between these numbering systems really easily as well. If we think about our binary number, our octal and hex numbers, we can convert really, really, really simply between them all. Once again, we're going to need to start with the number lines. We're going to need to, oops, what's happening there? We're going to need to start with the, not with the number lines, with the number grids. So once again, we'll do the bin hex 0, 0, 0, 0, 0, 0, 0, 1. And I'm also going to have to do the bin to oct. So again, 0, 0, 0. Now, do I recommend you do this every time? Yes. Why? Because it gives you the answers. I don't have to do any work from here. Okay, so I start with my binary. Now, everything through binary. Rule number 1, everything through binary. Just in case you missed that, everything through binary. Starting at the right, when I'm doing the hex, I highlight 4 numbers. So that's 0, 1, 1, 0. Highlight 4 numbers. 1, 1, 0, 1. Highlight 4, oh gosh darn, I've run out of numbers. So what do I do here? It's really simple. I add 2 leading zeros. Does it change anything? Absolutely not. So when I do my highlights here, 0, 0, 1, 0 is that. 1, 1, 0, 1 is that. 0, 1, 1, 0 is that. So 2d6 in hex. 2d6. Apologies for my atrocious handwriting. My tablet is getting very cranky at me when I put my hand on it. And that's pretty easy. I think that's very easy. So now when I do the same thing again, this time I'm going to do it in lots of 3, so I can get the octal code. And once again, I need two leading zeros. So 001, 011, 010, and 110. And so the octal for that is 1, 3, 2, that's a 2, 6. Easy. And that is how easy it is to do. So I'm going to pause and put the rest of the numbers in just to make sure I get it right. Before we do actually, the octal or hexabinary is really simple. Starting at the right hand side, we have 1. So that's always going to be 0, 0, 1. What is 4? 1, 0, 0. What is 3? 0, 1, 1. And now that I've got the binary, I highlight them into lots of 4. Once again, I have a leading character. That's a 0, so I can ignore that safely actually. 1, 1, 1, 0. What's 1, 1, 1, 0? E. 0, 0, 0, 1. E1. There it is. And so when I do the hex, same thing. What's B? B is down here. 1, 0, 1, 1. And what's 5? 0, 1, 0, 1. 0, 1, 0, 1. There's my binary. And once again, I'll separate this into lots of 3. And once again, I have a leading character I need. That's okay. Into the octal, 0, 0, 1 is still 1. 0, 1, 1 is 3. 0, 1, 1 is 3. And there you go. I've just converted between binary, octal and hexadecimal numbering systems. It's pretty easy.